Hey you guys, this is Mr. Millings, and in this video we are going to learn about something called equilibrium. So what is equilibrium and how does it work? Well, it says right here that most chemical reactions do not happen to completion forming products. For example, if we take a look at one type of reaction, combustion reactions are a type of reaction that happen to completion. So what does that mean? Well, we see this forward arrow here, and what this is telling us is that when we take methanol and we react it with oxygen, it's going to end up producing carbon dioxide and water. And the fact that this happens to completion, what this means is that carbon dioxide gas and water are not reacting with one another to produce oxygen and methanol. So a combustion reaction is a type of reaction that happens in one direction only, in the forward direction. So understand that concept. Furthermore, it says right here that most chemical reactions are in equilibrium with reactants forming products and products forming reactants. So most chemical reactions that we see around the world are not of this kind. Combustion reactions are a rare type of chemical reaction. Most chemical reactions are like this kind right here. They're equilibrium reactions, where reactants are forming products, as we see by the forward arrow, but products are also reacting with one another to produce reactants, as we see with the reverse arrow. And so it says right here that equilibrium is the condition a reaction has reached when the rate of the forward reaction equals the rate of the reverse reaction. And equilibrium does not mean that the concentrations of products and reactants are the same. Rather, it means that the ratio of the concentrations of products and reactants are the same. So if we take a look at these equilibrium reactions, most chemical reactions that take place around the world are of this kind. They're equilibrium reactions. Reactants are forming products, and products are also reacting with one another to produce reactants. And so when the rate of the forward reaction equals the rate of the reverse reaction, the system has reached equilibrium, and the ratio of the concentrations of these products and reactants will remain unchanged. So understand that concept. And so we have a few examples of some equilibrium reactions that we will talk about in later videos. For example, the Haber process, where we turn air into food essentially, and we'll talk about that in a later video. But that is going to be an equilibrium reaction where nitrogen gas is reacting with hydrogen gas to produce ammonia gas. But also what's happening is that ammonia is decomposing to produce hydrogen gas and nitrogen gas. In a later unit, we'll talk about weak acids and the formation of weak acids in our acid-base unit. Well, weak acids tend to look something like we see right here. Weak acid formation is an example of an equilibrium reaction, and same thing with the formation of weak bases. Weak bases are the formation of weak bases are also going to be an example of an equilibrium reaction where reactants here are forming products, but then these two products are also reacting with one another to form reactants that we see right here. And when the rate of the forward reaction equals the rate of the reverse reaction, the system has reached equilibrium, and the ratio of the concentrations of the products and reactants will remain unchanged. So let's take a look now at a visual aid that will help us to understand this concept of equilibrium. And so let's suppose we have two parking lots. We have parking lot A here, and we have parking lot B here. Initially in parking lot A, we have 6 red cars in this parking lot, and we have 14 blue cars in this parking lot initially. Furthermore, what ends up happening is that red cars are going to leave parking lot A, and they are going to turn blue as they enter parking lot B. What is also happening is that blue cars are going to leave parking lot B, and as they enter parking lot A, they're going to turn red. Furthermore, what we know is the rate. We can figure out the rate at which cars are leaving parking lot A and entering parking lot B, and we know the rate at which cars are leaving parking lot B and entering parking lot A. We can figure out the rate quite simply. We can take the initial concentration, which in this case is 6 cars per parking lot, and multiply it by K, our rate constant that we learned about in an earlier unit. And so if we take 6 times 0.3, we are going to end up with a rate of about 1.8 cars per minute, let's just say. And if we take a look at the rate that blue cars are leaving parking lot B and entering A, the rate here will be 0.450 times the initial concentration. And so the rate here is going to end up being 6.3 cars per minute. And so if we take a look, what we're going to notice is that the rate that cars are exiting parking lot B and entering parking lot A is going to be greater than the rate at which cars in parking lot A are entering parking lot B. And so what ends up happening is this: as more cars leave parking lot B and enter parking lot A, the concentration of parking lot A is going to increase. And if the concentration of parking lot A increases, then the rate of A going to B is also going to increase. And because if we take a look at parking lot B here, the concentration is going to decrease as cars leave parking lot B and enter parking lot A, the rate is going to decrease over here. And this is going to happen back and forth until these parking lots reach what is called equilibrium. And that's what we're going to have over here. If we take a look at the right hand side, we'll see that if this same trend happens over a certain amount of time, what will end up happening is that the concentration or the number of cars that are in parking lot A will level off at 12, and the number of cars that are in parking lot B are going to level off at 8, and these will remain unchanged because the rate that cars leave parking lot A and enter parking lot B, and the rate at which cars in parking lot B leave and enter parking lot A are going to equal one another. And if we take a look, we can see that's the case. At equilibrium, that is to say, once these concentrations remain unchanged, we can see that the rate here is going to end up being 0.3 times our concentration, which will be 3.6 cars per minute. And if we take a look over here, if we take our concentration times K, we will also end up with 3.6 cars per minute. So because the rate at which cars are leaving parking lot B and entering A, and cars are leaving parking lot A and entering parking lot B are equal to one another, equilibrium has been reached, and the concentration of cars in parking lot A and the concentration of cars that are in parking lot B will remain unchanged. So understand that concept, and we can apply this same concept to chemical reactions where we have reactants here, the red cars, changing into products here, the blue cars, and products here, the blue cars, changing into reactants here, the red cars. So understand how equilibrium works. Equilibrium is a condition a chemical reaction has reached when the rate of the forward reaction equals the rate of the reverse reaction, and the concentrations of those reactant and products will remain unchanged. So let's take another look at an example of equilibrium using this same concept. And so let's take a look at this second example. If we take a look at this second example, initially in parking lot A we have 18 cars, and in parking lot B we're going to have 2 cars, right? And so once again, the blue cars as they leave parking lot B and enter A are going to turn red, and the red cars as they leave parking lot A and enter parking lot B, they're going to turn blue. And so if we wanted to figure out the initial rate of the forward reaction and the initial rate of the reverse reaction, it's simple. We're going to take the concentration times our K value here that we learned about in an earlier video. And so we're going to take 0.743 times 18, and we'll see that our rate is going to end up equaling 13.4 cars per minute. So the red cars are going to leave parking lot A at a rate of 13.4 cars per minute. And if we want to figure out the rate at which blue cars are leaving parking lot B and entering parking lot A, we'll simply take the rate constant, which is 0.4, and we're going to multiply by our concentration, which is 2 cars, and we're going to end up with a rate of 0.8 cars per minute. So what's going to happen over time is that the parking lot here is going to reach what we call equilibrium. And if we take a look over here, what will happen over time is that as cars start to exit parking lot A and enter parking lot B, the concentration of parking lot B is going to increase. And if the concentration of parking lot B increases, the rate is going to increase. And so more cars are going to start to leave parking lot B and enter parking lot A, and this is going to happen over and over and over again until equilibrium is reached. At that point, the rate of the forward reaction is going to equal the rate of the reverse reaction, and we're going to end up with a scenario that we see right here. We're going to end up with 7 cars in parking lot A and 13 cars in parking lot B, and the concentration, or the number of cars in each parking lot at that point of equilibrium, is going to remain unchanging. It's going to remain the same. And so if we take a look here, if we take 7 times our K value to figure out the rate of our forward reaction here, we will end up with 5.2 cars per minute at equilibrium leaving parking lot A. And if we take 13 here times our K value, which is 0.400, we're also going to end up with 5.2 cars per minute. So because the forward rate reaction, or the forward rate of the reaction, is equal to the reverse rate of reaction, we say that this system here has reached equilibrium. Okay, so understand that concept, that the system here is going to reach equilibrium with 7 cars in parking lot A, 13 cars in parking lot B, and the concentration of these cars is going to remain unchanged unless you start to change things like heat or temperature, if we apply this to the concept of a chemical reaction. And the rates here are going to equal one another. The reverse rate going this way equals 5.2 cars per minute, and the forward rate going this way also equals 5.2 cars per minute. So understand that concept of equilibrium, and know how to apply that to chemical reactions and reactants and products. So now let's take a look at one last thing. Let's take a look at how we can graph an equilibrium reaction and take a look at what that might look like. And so we just took a look at equilibrium as we apply it to cars in parking lots, right? We said that if the initial concentration of cars in parking lot A is 18 and the initial concentration of cars, or blue cars, in parking lot B is 2, and we know the rates of the forward and reverse reactions, then this system here is going to reach equilibrium at 7 cars in parking lot A and 13 cars in parking lot B. And so if we wanted to graph this phenomenon, if we wanted to graph our red cars or our reactants and our blue cars or our products, it's going to look something like we see right here, where we have concentration of the products on our y-axis and time, usually in seconds, although we used minutes for this example here. Time is going to be on the x-axis. And so what's going to happen is this: in a chemical equilibrium, we're going to have reactants, right? A high concentration of reactants, and over time the concentration of reactants is going to start to decrease as these reactants form products. Also, what is happening is that products, right, initially there are no products, and so as the chemical reaction starts to happen, the concentration of our products is going to increase as reactants begin to form products. And eventually what's going to happen is that the concentrations of these two, products and reactants, are going to level out. They're going to remain unchanged. The concentration of our products is not changing at all here. The concentration of our reactants is not changing at all here as time goes on. And so right at this point right here, right at these 2 points, the system has reached equilibrium. Okay? And so let's suppose time here is 0 and time here ends up being, I don't know, 15 seconds. Then this right here would be a time of 5 seconds. So this system here reaches equilibrium at or after about 5 seconds. And so understand that concept where we have reactants forming products, and the concentration of those products is going to level off and remain unchanged. And then we also have reactants being consumed as they form products, and the concentration of those are going to decrease eventually to this point right here where the concentration levels off and remains unchanged. So at these 2 points here, we're going to have equilibrium. And so in this third example, it says 0.757 moles of A and 1.232 moles of C are added to a 1.750 liter container and reacted according to the reaction equation shown below. Find the concentration of A at equilibrium and determine the reaction rate at equilibrium. So we have a reaction, A going to C. It's in equilibrium with C, so C is also producing A. We know that the forward reaction has a rate equaling K times the concentration of A, and we know our rate constant is this right here for the forward reaction. We know that the reverse reaction has a rate equaling K times the concentration of C, and we know the rate constant for C is right here. And so what we have to do is we have to figure out the equilibrium concentration of A, and we have to determine the reaction rate at equilibrium. So if we take a look here, A is going to C at this initial rate, right? We also know that C is going to A at this initial rate right here. And so we have to figure out the concentration of A at equilibrium and determine the rate of the reaction at equilibrium. So what we need to do is we need to think about what's happening here. First of all, if we think about it, this is a closed system here, meaning that we're not adding any more reactants or products as time goes on, and we're not removing any reactants or products as time goes on. So if we think about it, the initial concentration of A plus the initial concentration of C should equal the equilibrium concentration of A plus the equilibrium concentration of C. So this is one way that we can think about what's happening in this closed system. The initial concentration of A plus the initial concentration of C is going to equal the concentration of A at equilibrium plus the concentration of C at equilibrium. Furthermore, we know that at equilibrium, we know that the rate of the forward reaction is going to equal the rate of the reverse reaction. That's what equilibrium means. The forward and reverse rates equal each other. So if we take a look here, K times the concentration of A at equilibrium is going to equal K times the concentration of C at equilibrium. So we can use these two formulas here to figure out the concentration of A and then determine the reaction rate as well at equilibrium. So the first thing that we should do is probably find the concentrations of our reactants or reactant here and our product here. And so if we take a look, to get the initial concentration of A, we are going to take the number of moles of A, since we're going to find this in molarity, and molarity equals moles per liter, we need to figure out the number of moles of A, which is 0.757. And we're going to divide this by the volume of our container, which is 1.750. And when we put this in our calculator, we're going to end up with 0.433 as the initial concentration of A. Let's now figure out the initial concentration of C. If we take a look, the initial amount of moles of C is going to be 1.232. 1.232. And we're also placing this in a 1.750 liter container. And when we put this in our calculator, 1.232, and divide this by 1.750, we are going to end up with 0.704. So we now know the initial concentrations. And so what we can do here is we can plug these numbers into this formula that we see right here. And then what we can do is solve for this variable right here, the concentration of C at equilibrium, and then plug it into this formula right here, and then solve for the concentration of A at equilibrium. So let's go ahead and do that. Let's go ahead and solve this problem. Let's go ahead and use this formula right here to figure out and isolate the concentration of C at equilibrium. So the concentration of C at equilibrium is going to equal the concentration of A initially plus the concentration of C initially minus the concentration of A at equilibrium. And so if we take a look here, the initial concentration of A is 0.433 plus the initial concentration of C, 0.704, minus the concentration of A at equilibrium. And this is going to be the concentration of C at equilibrium. And so when we put this in our calculator, the concentration of C at equilibrium is going to be equal to 1.137 minus the concentration of A at equilibrium. And so what we can now do with this right here is we can now substitute this for this right here in this formula that we see right here. So we're going to substitute this whole expression for this right here. So let's go ahead and do that. Write down here, first of all, K times the concentration of A at equilibrium. So here's our K value. K doesn't change. Whether it's the initial concentration or equilibrium concentration, K is always going to stay the same unless temperature is increased or decreased. But it doesn't say that here. So let's figure this out. Our K value here is 0.452. And we're going to go ahead and leave off the units when we're doing this calculation. Times the concentration of A at equilibrium. This is going to be equal to K times the concentration of C at equilibrium. So we have to use our K value for C, which is 0.787 times the concentration of C at equilibrium. Well, the concentration of C at equilibrium is right here. We are now going to fill this in for the concentration of C at equilibrium. 1.137 minus the concentration of A at equilibrium. And we're going to end up with 0.452 times the concentration of A at equilibrium equaling this times this, 0.787 times 1.137 is equal to 0.895. Minus 0.787 times the concentration of A at equilibrium. Guess we don't need the parentheses here. And so we can now start to combine like terms. If we add 0.787 to this side, 0.787 minus 0.787 is going to equal 0. And if we add 0.787 times the concentration of AEQ over here, we're going to end up with 1.239 times the concentration of AEQ equaling 0.895. So how do we isolate the concentration of AEQ? We are going to divide both sides by 1.239. And so if we do that, we will end up with, we're running out of room right here, so we'll do this up here, the concentration of A at equilibrium equaling 0.895, all divided by 1.239. And we'll put this in our calculator, and we will end up with 0.722 molar. So going back to our original question, we were asked to figure out the concentration of A when this system here reaches equilibrium, the concentration of A at equilibrium is going to equal 0.722 molar. And so the second part of this question asks for us to figure out the rate of our reaction at equilibrium. Well, in our last step here, to get the rate at equilibrium, here is our formula, right? Our formula is going to equal, the rate is going to equal K, which we know is 0.452, times the concentration of A, which we just figured out is this, at equilibrium, times the concentration of A at equilibrium. So 0.452 times 0.722, and we're going to end up with 0.326. And since this is a rate for chemical reactions is usually going to be expressed in molar per second or moles per liter per second. So to answer our final question, what is the concentration of A at equilibrium? It's 0.722 or 0.722 molar. And what is the rate of the reaction at equilibrium? Well, the forward rate is going to equal 0.326 molar per second. And since at equilibrium the forward rate equals the reverse rate is also going to equal 0.326 molar per second. So if you like what you see, go ahead and click that little bomb in the bottom right hand corner, and that will subscribe you to my channel. And feel free to leave any comments or questions in the comment section down below. And I really hope you guys found this helpful.